If you're building RAG pipelines, then here's a problem statement that you're going to run into sooner or later. The document that you're looking for is in the index, your query is accurate, and yet your retrieval still can't respond accurately. You start questioning the embedding model, the LLM, and tweaking the prompt for the third time this week. But of course, none of that is the problem. The problem is something that you decided before you ever ran a query. And that's how you cut your documents into chunks. Because here's the thing that very few tell you when you start with RAG pipelines. The chunk is the actual unit of retrieval. So your vector database can only ever hand you back a chunk. If the answer to your question is not neatly packaged within a chunk, it doesn't matter how good your database or your embeddings really are. The answer was never really on the table in the first place. Because certain RAG pipeline design choices that you make early on, such as the embedding size and the chunking strategy, truly does impact the accuracy of your retrieval. And in this video, we're going to be focusing on chunking strategy. We're going to take the same documents, the same database, the same query, and change nothing but the chunking size and look at how the results differ. I'll give you a framework so you don't have to guess at this ever again. What does chunking actually do? Let's get the mental model right first. Chunking is a step that happens before anything gets embedded. In plain language, you take a source document and you split it into subparts or segments. And each of those segments is what we then refer to as a chunk. And you can choose how you wish to do this chunking breakdown for each document. And these chunks is what then gets embedded and stored into our vector database. A single document does not become one single point in your vector database. It becomes many points, one per chunk. When a query comes in, it gets embedded with the same embedding model and then compared against the other chunk vectors. The database then finds the closest chunk vectors and returns the relevant chunks. Which means that the search is actually happening on the predefined chunk, not on the document itself or a particular sentence. That's why it's fundamental to understand how you decide to create your chunks. The reason that chunk size matters is because there are two main failure modes and they each pull in different directions. First failure mode is that the chunk is too small. You split at 128 tokens. Now imagine a 4-step procedure in a technical manual that describes a restore from backup, configuring an index, and at 128 tokens, that procedure gets sliced across 3 or 4 chunks. The retrieval may match one of them, hand you step 2 and 3, and then the setup verification step are just gone. What you end up getting is a fragment, which is still technically correct, but it's an incomplete response. Failure number 2, however, is that the chunk is too large. Now you overcorrect and you go to 2048 tokens. This chunk may have 5 different topics buried into it. If you're lucky, the query may match the chunk because one paragraph is relevant in it. However, the embedding is an average of all 5 topics. So the signal that you're actually looking for is diluted and you retrieve the wrong section of a long document. Too small and you lose context, and if it's too big, you lose the precision. So the right chunk size is the one that contains the right information and not much more. So how do you choose the starting point for your chunk size? The good thing is that you don't have to guess at this because people have actually measured this. And this study actually surprised quite a few people. The Flowtorch and Vector benchmark from February 2026 run across 50 academic papers put recursive 512 token chunking at 69% retrieval accuracy versus 54% for semantic chunking. Now, semantic chunking means that you're splitting up the chunks based on where a topic starts and ends naturally within a document. And it sounds smarter, right? Instead of just splitting at a certain token, you split it at the meaning. What they found was that on technical documents, it often produces tiny fragments at around 43 tokens. And tiny fragments, they tank retrieval accuracy for the same reason that we discussed in failure mode 1. It technically is a correct answer, yes. It provides an incomplete response. What they also found was that overlap, which means that you pad your chunk with some of the text from the previous chunk and the following chunk to ensure that the context is intact, actually is helpful in some cases, but also adds cost in other cases. It's not free and it's not magic. This highlights that all of these are just starting points, but it's not law. All right, enough theory. Let's have a look at this in the code. In practice, we're going to be running the same type of retrieval pipeline that we've been doing in our earlier videos. As you can see here, we have a Docker container with an instance of Actin VectorAI database running on our computer. And in our repository, we also have a technical documents folder here with information about backup and restore, distance metrics, and indexing. We are going to chunk these documents, and we're going to do that with our chunker function here. And this chunker, it takes in a text, the decided token size, and what overlap we wish to have on each end of our chunk to be padded. And it really chunks this document up just based on the token size. We are splitting on real tokens using the same tokenizer as the embedding model that we're going to use. 128 tokens means exactly the number of tokens that the model would count. Based on this tokenizer encoding, the function returns a list of chunks that encapsulates the entire source document. Now, if we go into our ingest file here, we're going to be importing our chunker and defining the embedding model that we're going to be using. In this case, we're going to be using the English version 1.5 of BGE Small. The build point function here is going to then chunk up the documents and embed them using the model and return a list of point structs which we're going to upsert into our collection. If you take a look at our main function, you're going to see that we are going to create a VectorAI client which is going to generate two collections based on which chunk we are testing. So in this case, we're going to check for 128 chunks and 512 chunks. And the load collection function checks whether this collection already exists. If not, it creates it. And it also calls this build points function, which is going to create the points that we're going to upsert. So we're essentially creating two different collections here that are using the same source documents. The only difference is the chunk size, whether it's 128 tokens or 512 tokens. That's the factor that we're isolating in this whole experiment. And we're going to be running then Python 3 ingest. You see then for both collection, it has ingested 14 chunks for the smaller chunk size 128 and 5 chunks for the 512. And with that, we can also check the collections in our VectorAI database UI, and you'll see that both of them have been populated with chunks. See that the 512 collection has bigger chunks here. Now, the next step is going to be the comparison, which it will be our moment of truth, because we're going to be running a query to ask, how do I actually restore a collection from a snapshot, and how do I do that step by step? You know, intuitively, you would like to have a procedure on how this is actually done step by step. However, we will see how the chunking sizes impact the chunk retrieval that happens. After that, we're going to be using a compare script, which is going to take in a default query and embed it using the same model as here, and it's going to search the collection that we have in question. So in our case, it's going to take in the query and search it in both collections before returning the answer. So when we run this, let's go ahead and see what happens. The query that we are asking is, how do I restore a VectorAI database collection from a snapshot step by step? And this shows that 128 token chunks, they perform well, but it directly goes into the snapshot procedure and order of the steps matter. So the longer 512 token chunk, however, gives you the actual operation manual. So it gives you the full procedure that you need to follow to actually restoration of the collection from the snapshot. Here you see how the chunking size actually becomes a difference between getting a useful answer and a fragment of a technically correct answer. So the argument of this video sits in that terminal. Decision that you make on chunking size before you ingest any documents or run any query is crucial for your retrieval accuracy. In the end, how do you actually choose your chunking size? There's a framework that I would start every project with. Our initial default should be at 512 tokens with 10 to 15 token overlap. This is the standard setting that is right more often than anything else. If your queries are more factoid, then go smaller to 128 to 256 tokens. So for details such as names, dates, definitions, short lookups, where the answer is one fact and a bigger chunk would just add noise. Or if your queries are more analytical, then go bigger, up to 1024 tokens. And this is when the answering requires reasoning over one or multiple paragraphs. Then the rule that overrides it all: make sure to test your chunking size before you commit. The only thing a framework can provide you is a starting point. Making sure that you test this in advance is going to save you for headache much later. Let's wrap it all up. Chunk is a unit of retrieval for vector databases. It sets a hard ceiling before any query runs. If you have too small chunks, you lose context, but if you have too big chunks, then you dilute the signal. Starting point should be at 512 tokens with 10 to 15 tokens in overlap. Most importantly, make sure to test everything on your own data before you commit. In the next video, we're going to be putting this to use when we build an AI agent second brain using OpenClaw and VectorAI database. And the chunking strategy is going to go straight into that memory layer.
If you're ready to start building, make sure to not miss a sign up where you can get 1 million vector embeddings for free for 30 days.
And if you have any questions, the team is available on the Discord link that you'll find in the description. I'll see you in the next one.